Transmission lines, problems on secondary constants, series on transmission line theory, lecture number 1.22. Propagation constant and characteristic impedance. These two are called secondary constants of line. Propagation constant is complex quantity. It has a real part. It is called attenuation constant. Imaginary part is called phase shift constant. In this session, we consider several problems which are based on basic characteristics of propagation constant and characteristic impedance. To begin with, we consider a problem, example 1. Determine the propagation constant from the following data. Current falls to 1/50 of its value in 1 kilometer. Length of lambda by 4 long line is 5 meters. B. Frequency is 50 megahertz. Attenuation is 2 decibels per meter, velocity factor is 0.8. C. 500 megahertz frequency, R is 2.5 ohms per meter, G is 0.0 ohms per meter, Z0 is 100 ohms, dielectric constant of insulation is 2.50. D, last one, frequency is 1 gigahertz, voltage drops from 10 volts to 9 volts in 100 meters, dielectric constant is 2.25. Now, solution. A. First part. Current falls to 1/50th of its value in 1 kilometer. Length of lambda by 4 long line is 5 meter. Attenuation A in Nepers per kilometer is, A is natural logarithm 50, it becomes equal to 3.91. Attenuation in Nepers per meter is attenuation constant alpha, hence alpha is 3.91 by 1000. It is 3.91 millinepers per meter. See, current is falling to 1/50th of its value in 1 kilometer. So, A attenuation in a Nepper per kilometer is natural logarithm 50, but it is Nepers per kilometer. But we want in meters, so we have to divide it into by 1000. It gives to the 3.91 millinepers per meter. Length of lambda by 4 long line is 5 meters. Therefore, wavelength becomes 20 meters. It is so simple, so obvious. Beta by definition is 2 pi by lambda. Lambda is known, so beta becomes 0.314 radians per meter. Alpha is available, beta is available. Now gamma is simply alpha plus j beta per meter units. B. Frequency is 50 megahertz, attenuation is 2 decibels per meter, velocity factor is 0.8. This is the given data. Attenuation Nepers per meter is attenuation constant alpha, hence alpha is, see here attenuation is given in decibels, but attenuation constant that is to be used in propagation constant, it should be in Nepers per meter. So we have to convert it into Nepers per meter. 2 divided by 8.686 converts dB into Nepers, resulting in 0.23 Nepers per meter. Angular frequency is omega, 2 pi f is available, so omega is available. Velocity, wave velocity is V, velocity factor multiplied by C. Velocity factor is given, C is 3 into 10 power 8, so B is known, so beta is omega by V. Omega is available, V is available, substitution results in 1.31. So alpha is available, beta is available, it means gamma propagation constant is available. It is 0.23 plus J 1.31 per meter. In C, part C, frequency is 500 megahertz, R is 2.5 ohms per meter, G is 0 ohms per meter per Siemens per meter. Characteristic impedance is 100 ohms. Dielectric constant is 2.50. Attenuation constant in Nepers per meter is given by alpha equal to half R by Z0 plus G Z0. This is for low loss lines. So it results in from the available data, substituting the available data, one can find out alpha equal to 0.0125 Nepers per meter. Angular frequency 2 pi f, it can be easily found as 10 power 9 pi. Wave velocity is, of course, C by square root of epsilon r. Phase shift constant, therefore, beta is omega by B. Omega is known, V is available, so beta is also known. So, therefore, gamma is 0.0125 plus J is 16.56 per meter. Now D. Frequency is 1 gigahertz. Voltage drops from 10 volts to 9 volts in 100 meters. So this particular piece of data gives information pertaining to alpha. Dielectric constant is 2.25. This gives information pertaining to wave velocity or beta. So this is alpha information, this is beta information. Attenuation A in Nepper per 100 meters is in Neppers. It is A equal to natural logarithm 10 by 9, 0.105. This is for 100 meters. For 1 meter in Neppers, it becomes 0.105 by 100. Angular frequency is 2 pi f. F is available, so omega is known. Wave velocity V is c by root epsilon r. C is known. 3 into 10 power 8. Epsilon r is known. It's a phase shift constant, which is omega by V. It can be computed as 31.42 radians per meter. So alpha is available, beta is available. So propagation constant can be considered. These problems are set around the internal physics of alpha and beta. We consider another problem, example 2. Find the input impedance and Ci of a long uniform line. Long means infinite line. Working at 1 kilohertz when it is driven by a voltage source of 100 volts and current into the line is 60. Angle is 0.34 milliamperes, and when B, its primary constants are R 10 ohms per kilometer, L 3.7 millihenry per kilometer, C 8.3 nanofarad per kilometer, and G 0.4 micromos per kilometer. In case of B, also determine phase velocity and wavelength over the line. Now the solution procedure. A. Input impedance is a ratio of input voltage to input current. So input voltage is known, it is 100 volts. Input current is also known, it is 60, 0.34 milliamperes. This is angle. So input impedance one can easily find by considering the ratio. The line is long. Note the line is long. So we can consider it as an infinite line. So input impedance of infinite line is characteristic impedance by definition. Therefore, characteristic impedance of the line is input impedance, which is 1.67 angle minus 0.34 kilo ohms. We consider B part. B part is primary constants are given and we are asked to find out input impedance and characteristic impedance. As the line is long, input impedance is equal to characteristic impedance. This is the basic point around which the problem is designed. This particular problem is composed. It can be found as follows. From the given values, reactance of L, susceptance of C can be found. Omega L, omega C. L is given, C is given, omega is given because frequency is given. 1 kilohertz is the frequency. So F is given, omega means 2 pi F. Substitution and a little bit of manipulation results in reactance and susceptance of C. The values of Z and Y, and from them the Ci Z naught can be found as Z is of course R plus J omega L, Y is G plus J omega C. R is known, omega L already calculated, G is known, omega C we already calculated. Substitution results in values for Z and Y. But Z naught by definition is square root of Z by Y. Substitution and a little bit of manipulation results. Z naught as 696.42, angle is minus 0.199 ohms. The PC propagation constant can be found as gamma equal to root ZY. So Z is known, Y is known, ZY can be computed and put in rectangular form as 10 power minus 3 multiplied by 7.60 plus J 35.53 per kilometer. Velocities B over the line can be found from 1 by root LC, but it gives exact value only when the line is lossless. But an approximate value when the line is a low loss 1. For all types of lines, however, exact value for a velocity can be found from the ratio of omega by beta. Given the line is a lossy one and hence phase velocity over the line is, we have to use omega by beta. that ratio to find B, not 1 by root LC. 1 by root LC is for lossless line. For any line, general line, the expression is omega by beta. Omega is known, beta is known, therefore B is 1.77 into 10 power 8 meters per second. The wavelength over the line is lambda is 2 pi by beta. Beta is 2 pi by lambda, so lambda is 2 pi by beta. It is 177 kilometers. We consider another problem, example 3. Find PC of a finite length uniform line terminated over its characteristic impedance. When working at 1 megahertz, it has currents 10.20 angle minus 0.34 milliampere, 10 angle 0 minus 0.40 milliampere at 2 points separated by a distance of 0.2 meters, 2 meters. And when working at 1 kilohertz, its primary constants are R, L, C, G values are given. So A, we are asked to find out PC, A, B. Two parts are there in this problem. In A, again 2 parts are there. Distance 0.2 meters, distance 2 meters. Right. So solution A. First we consider A. PC is combination of attenuation and phase shift constants. Attenuation constant alpha is natural logarithm IS by IR. IS means sending end current, IR is receiving end current. When these points, sending end point and receiving end point, are separated by unit distance. That is the way alpha is defined. So now natural logarithm 10.20, this is sending end current, 10 is receiving end current, it is 0.0198. But these points are separated by 0.2 meters in the first case, in the second case 2 meters. So attenuation constant, naturally here it is neppers per this many number of neppers per 0.2 meters. Okay, right. B, beta. Beta is by definition angle of IS minus angle of IR. When already mentioned, sending and receiving end points are separated by a distance, 1 unit distance. But first we consider 0.2 meter distance. So IS, angle of IS, angle of IR, they are available. Substitution, it results in 0.06 radians. Assuming that 0.34, 0.40, these are radians. Here 0.06 is radians. So gamma is alpha plus j beta, this one. As already mentioned, the alpha and beta here are values for 0.2 meters. 0.2. Propagation constant gamma obtained above is for points separation of 0.2 meter. Then for 1 meter, it becomes gamma by 0.2. In case gamma obtained above is for points separation of 2 meters, then for 1 meter, it becomes 0.0198 plus j, 0.06 by 2 meters. The phase velocity is omega by beta. Omega is known, frequency is known. Beta we have already calculated. Beta is when 0.2 meters separation, beta is 0.3. Using that we have this velocity. When separation of points is 2 meters, then we have to use this 0.03 beta value as beta. So it results another velocity. Now B part. From primary constants, PC can be computed as shown below from the given values, omega L, omega C. L is available, C is available, frequency is available. So omega L, omega C can be calculated within no time. So Z and Y. Z is R plus J omega L. Y is G plus J omega C. R is known, omega L is known, G is known, omega C is known. This is complex quantity. So we can substitute and find Z and Y values. Once Z and Y are known, gamma is square root of ZY, resulting in 7.392 into 10 power minus 3 plus J 0.035 per kilometer. The phase velocity then can be found as V equal to omega by beta. This is frequency, this is beta. Now, and it results in 1.79 into 10 power 8 meters per second. Note, the beta here is, this is radians per kilometer. So if we substitute, the result which we get is kilometer per second. That thing is converted into meters by multiplying it with 10 power 3 ultimately what we have for velocity is 1.79 into 10 power 8 meters per second. So this is what I want to share for now with you. You can notice that all these problems are designed or composed to illustrate the basic features and physics and the ideas behind the definition of these constants, secondary constants of the line. Enough.